The last speaker of this session is Morgan Lynch. He's from Seoul National University, and he's going to talk to us about experimental observation of acceleration in the induced thermality. Morgan, you have 20 minutes, and I'll give you a warning 2 minutes before. So whenever you're ready, the floor is yours.
Okay, well, thank you very much for the opportunity to speak. I just learned about this conference yesterday, and I reached out to Eduardo if I could present, so thank you for the opportunity for that as well at short notice. Let's talk a little bit about this observation of acceleration-induced thermality. This is an analysis I did on a particle physics experiment that was carried out by the CERN NA63 collaboration. So let's talk a little bit about what motivated me to look at this, right? So the general idea is to look at particle physics by using techniques from quantum field theory and curved space-time. And so the general idea with that is that we want to incorporate things like the Unruh effect, things like Unruh DeWitt detectors, and apply these types of things to Larmor radiation and to develop certain classes of observables such as Larmor power spectrum and things like that. And then so what we want to do then is apply that to these channeling radiation experiments by NA63. And so the general idea for this project was to basically look at particle physics experiments, but rather than looking at, say, momentum transfer from a collision, we look at strong or extreme accelerations using semi-classical vector currents. And so let's see what accelerated QED has to say about this high energy channeling radiation. So to begin, let's go ahead and have a quick review of the Unruh effect and Unruh DeWitt detectors. As you recall, what Unruh had done was to look at the near horizon limit of a Schwarzschild black hole and put a particle in a box really close to the horizon and absorb Hawking radiation from it. And that near horizon geometry is equivalent to uniformly accelerated motion in Minkowski space, where now rather than absorbing Hawking radiation from the Schwarzschild horizon, you can absorb Unruh radiation from the Rindler horizon that you see from a uniformly accelerated reference frame. And so to classify these types of interactions, we have things like, for a massless scalar field, we have our interaction action which is coupled with our scalar field and the monopole moment operator of our detector, which is like a creation and annihilation operator, which induces transitions in the detector. And so if we start off in vacuum, we look at the transition of our detector from some initial state to some final state, accompanied by the simultaneous emission of some particle phi. And the response function, or the transition rate per unit time of this detector, is given by the Fourier transform of the two-point function of the particle that's emitted. And if you evaluate it along a uniformly accelerated current, you get a thermal transition rate, where the temperature of this is the celebrated Fulling-Davies Unruh temperature. And so the idea that we want to do is to take this class of thermalized accelerated observables that we see here and apply it, or we'll first bump it up to the QED interaction and then apply it to these experiments. So with that in mind, let's go ahead and look at this experiment. This is a high energy channeling radiation experiment, okay? And what we have is 178.2 GeV positrons, so high energy positrons, which are fired into samples of single crystal silicon. And so to give you an idea of what's happening, so this is what's known as channeling radiation. So the positron penetrates the crystal along an axis of symmetry, and the repulsive sites of the crystal and lattice acts as a harmonic potential in the transverse direction. And so as the positron moves through, it'll oscillate in a harmonic, as a harmonic oscillator transversely, emitting radiation. And so when you could add up all the radiation or collect all the radiation from the experiment, that's these black dots here, that's the data points. This is a power spectrum, that's energy per unit time per unit frequency. Okay, so this is their data set. This is a 3.8 millimeter thick crystal, by the way, a very thin crystal. And here you see the standard catalog of radiation reaction models. So this is things like Landau-Lifshitz equation, Lorentz-Abraham-Dirac equation, and various Monte Carlo simulations of those equations applied to the data set. And so just off the bat, we see that these things aren't really looking too well whenever we apply them to the data. And so the idea then was to look at this data set, but using this thermalized observables that we get from the Unruh effect. And so look at our Larmor power spectrum. So the first thing we want to do is generate the observable that they have measured. So we start off with the QED interaction here. This is our photon field coupled to the semi-classical vector current of the positron, which is coupled to an Unruh DeWitt detector as well. And so we have the QED response function now, which is the standard Fourier transform of the Whiteman function, except now we have our essentially the V dot A interaction, or the square of the V dot A interaction here. And so evolving it along the uniformly accelerated trajectory, we compute our power spectrum, which is this expression here. The interesting thing to note about it is that it's just comprised of these Hankel functions. And there's a mathematical identity from these Hankel functions where if I switch the sign in the index, which is equivalent to switching the sign of the detector, meaning transition up or down, it'll spit out this exponential term as a math identity of the Hankel function. And you can see just by eye that it's the Boltzmann factor of thermal equilibrium at that Fulling-Davies-Unruh temperature. So this is a rigorously thermalized power spectrum, okay? And so this is the thing that we want to apply to the data set. Also at the same time, because of that thermality, we could look at the Rindler frame process. So this is the Minkowski process. Let's look at the Rindler frame process so that we can tie it specifically to the Unruh effect. So this is a paper from Cozella et al., all of the guys down in Brazil, Matsas and Banzella and Landolfo as well. And so what they had looked at was if I have a co-moving oscillation, just like what we have in this channeling oscillation, right? The co-moving frequency will resonantly couple to Rindler particles in the Rindler bath at that same frequency, gauged by the amplitude. So it's amplitude by that frequency. And so you get this resonant emission and absorption specifically from that thermal bath. And so when you look at that, right, so the probability of the absorption of that particle from the bath, probability of emission, and the total probability gives you this thermal factor, which is simply just the sum of these two terms here, okay? And we can leave the temperature of that Rindler bath arbitrary for the time being, right? So this is from the Rindler side. On the Minkowski side, you have the statement of detailed balance, right? You have the transition down is equal to the transition up with the exponential from the thermal factor here. And then so the total emission probability, it gives you this. So this is the statement of detailed balance from the Minkowski side. Now, since these two processes should be covariant descriptions of the same process, right? So these things are going to be the same thing, right? The statement of covariance here gives us this expression, right? So this statement of detailed balance from the Minkowski side is precisely that statement of that resonant emission and absorption from the Rindler bath of those Rindler particles. And if you substitute in that Rindler temperature as the Fulling-Davies-Unruh temperature and that Rindler frequency as the energy gap, it collapses identically to that statement of detailed balance. And so what that enables us to do is to unwind that detailed balance back into a statement of thermality, but at an arbitrary temperature. And so then what we can do is directly measure that Rindler temperature from the data set. So it gives us a way to actually measure that temperature directly. And so if we employ that, okay, hi, sorry. And so if we employ that, here we have our power spectrum with that explicit thermal term here. And then how we compare to data now, first of all, we need the acceleration, right? So since we're looking at recoil acceleration or radiation reaction, we expect to have a recoil acceleration, which is produced by the kick from the photon emission. Okay, so that's an idea to prompt us to look for that acceleration. Best fit parameters, we have an overall scale factor to take into account detector efficiencies, that acceleration that we measure, the Rindler bath temperature we measure. So the energy gap now, in the idea of recoil, which is what we take from an example of Cherenkov radiation, you just expect something like a recoil acceleration from the kick, or a recoil kinetic energy, excuse me, as our energy gap. So that's just one of the terms. And so what we did was we adopted just a general polynomial energy gap. We have a constant term, which should be the channeling oscillation. We have this term linear in the omega, which should be that fiducial Rindler term, which resonantly couples from the Rindler bath. The A2 term should look like a recoil. And then we included an additional cubic term, just as we don't have any intuition for what it is, but we wanted to include just one more, just beyond our knowledge. But that one we don't have any intuition for, probably some cross term. And so then we do a best fit and compute the chi-squared, so the goodness of fit to that data set. First thing first, though, we have to make sure that our system has time to thermalize. Okay, so 3.8 millimeter thick crystal with a positron essentially moving the speed of light through it, right? That's our thermalization threshold. And here is the thermalization time for that theory. And we see that there's going to be a thermalization threshold at about 22 GeV. And then when we compute the chi-squareds, the best fit, we see a rapid convergence of that chi-squared to within the 1 standard deviation threshold as soon as we pass over that thermalization threshold of the 22 GeV. And so what this means essentially is that the theoretical curve lies inside of the error bar of every single data set. And so historically speaking, that thermalization time has kind of been ruining all of the previous attempts to measure this Unruh effect. But we do have a 22 GeV thermalization threshold, and we see that rapid convergence of the chi-square to 1 above that threshold. Okay, so now let's look at that first cutoff that gives us that good chi-squared here. So the 30 GeV cutoff applied to the data set. So here on the left is that standard catalog of radiation reaction models. Here on the right is the thermal theory applied to it, okay? So here is the cutoff, here is our best fit. So everything above this curve is thermalized, everything below is not thermalized. right? And if you look at the chi-squareds of all of these radiation reaction models compared to the accelerated QED analysis, it's the only one with a chi-square that's even remotely good. And in fact, within that 1 standard deviation threshold. One thing that's interesting is that this portion right here is not thermal. It's pure channeling radiation. This portion is thermal. And so you get this really weird window into that onset of thermality where you have a data set where some of it's thermal, some of it's not. And so there's maybe a potential window into that information loss. Some of this information here has been burned away. Some of this information is still channeling radiation. So it's a really interesting system that we have here. So let's look at it a little bit more at the best fit parameters, okay? First things first, in our best fit parameter, if you look at the 22, where that cutoff should be here, this is a normalized data set. So if you look at that, that's about a 12.9. So that's our overall scale, okay? The acceleration, recall, comes from that kick from that recoil acceleration. So if you just look at a standard example of our photon frequency for 100 GeV photon, that should give you about a 6.2 PeV acceleration. And our best fit acceleration for the system is comparable. So that's going to be some smearing from the kicks from these photons, but we get something that we would expect. The A naught, which is that channeling oscillation term, this is in units of GeV, but with the boosting, this is about 5 electron volts in the co-moving frame. So this is standard for channeling oscillation. But then we have this fiducial Rindler term, which is this A1 term here. So that's the frequency of oscillation multiplied by the amplitude of that oscillation. So if I just take the lattice constant for silicon, 2 minutes, okay, multiply by that lattice constant for silicon, I get 0.011, and best fit parameter is this right here. So that confirms that Rindler term, okay? And so that gives us kind of that fiducial energy gap that we got, the channeling term, that fiducial Rindler term, and this recoil term, right? If you look at the recoil acceleration or the recoil kick, we have at least something in agreement for that, recoil kinetic energy term. And then directly measuring the temperature of that Rindler bath, right? This Fulling-Davies Unruh temperature here comes from averaging the acceleration across these data sets here. And then the best fit Rindler temperature is the one that we directly measure. These data error bars come from just the standard deviation of the mean, but we were able to confirm that that Rindler temperature is that Fulling-Davies Unruh temperature with an upper limit of a 2.23 PeV temperature from the highest photon frequency. Okay, and so that's the fact that we were able to measure that Rindler temperature, that's the confirmation of that experimental proposal put forth by Koczela et al. For measuring the Unruh effect. And then to confirm this, we look at the thermodynamics of space-time. So since we have the Unruh effect, that means we have a Rindler horizon. And so that means that if we're putting photons through that Rindler horizon, we should see the change in the Rindler horizon area in accordance with essentially the Bekenstein-Hawking area entropy law. And so if you look at the second law, we can integrate up to get that area entropy ratio. And then whenever we integrate that data and plug it into the expression, we see the convergence of that area entropy ratio to 4 Planck lengths above that same 22 GeV threshold, okay? And so we have this independent analysis, both with the same thermalization threshold from both the chi-squared of the power spectrum and then of that area entropy law by integrating the data. And so I guess I could just kind of quick finalize just some recent work I've done. I've kind of extended this recoil to graviton emission for, I was looking at binary inspiral for gravitational wave emission. And so we have our graviton response function, and I incorporated that recoil kinetic energy there, and I was able to reproduce the Peters-Matthew equation for graviton emission. Yes, ma'am.
Yeah, you're over time now. Can you just
okay, cool. All right, so we're done. And so conclusions, so there you go. So we were able to basically measure the Unruh effect, or what looks like is a preliminary analysis, which measured the Unruh effect at that NA63 collaboration. So thank you very much. Yeah.
Thank you, Morgan, for the nice talk. I wonder if someone has questions, quick questions for Morgan now. Oh, yes, Albert, go ahead.
Yes, so I guess I would need a bit more time to digest this and formulate the question properly. But somehow what's bothering me is, you know, to have a clear-cut observation of an effect like the Unruh effect, one will need a sufficiently long time. I understand that the accelerations here are very large, maybe, but so. Can you elaborate a bit more on how to interpret this properly? Because you get a kick, which is kind of a sort of instant kick almost. And so how, well, you have a collection of those, but okay, so yes.
Yeah, so basically the idea is you have a statistical buildup. So you have a high, basically a high luminosity beam. And so each of these positrons emits only one photon. There's actually a filter on the experiment, so that's only a one photon emission event that they consider, right? So as each of these photons gets emitted, there's the humongous kick from each one of them. And then statistically, these things all build up to produce essentially like a uniformly just accelerated single positron that's emitting photons in that sense. And so it's using the high statistics of the experiment to build up the thermalization time, or the thermalization. At the same time, we also have time for the system to thermalize just based off of the thermalization time itself for those accelerations. So you have the high statistics, each one that builds up, and then you have for the crystal size itself enough thermalization time for this statistical acceleration.
So if I understand correctly from this picture and what you were describing, it's not that you have, each one of these positrons as being a system that would have a natural one-to-one correspondence with the usual sort of description of the Unruh effect, but it's a sort of effective description for the collection of all the positrons that then statistically you can somehow match that to what a response that would be equivalent to that of a single detector going through uniform acceleration.
So I guess so. Yeah, I mean, I'm sure that there's going to be some way to show it explicitly, but yeah, it's the fact that each one of these things, I believe, I guess I should say that. Yeah, I mean, so far as I understand, it's just, it's a single event that builds up to present the thermality there. I mean, it's not one detector that's uniformly accelerating for forever that you see the thermalization. It's each one emitting a photon, and then all of those build up the same statistics, which is equivalent to if it was just one, Now, how to show that, I'm not too sure, but I mean,
so by the way, I mean, so that was maybe not entirely clear to me, but the effect that you're looking at is at the emitted radiation itself, or the effect of that somehow on these accelerated particles? Because that's also another subtle issue, which is that the Unruh effect per se is the effect on the accelerated detector, so to speak.
So yes, I mean, okay, yeah.
But of course, there is something which is kind of related, but not exactly the Unruh effect, which is whether this accelerated detector, which is undergoing this excitation and de-excitation, from the inertial point of view, whether that is emitting some kind of radiation. So the question is, the phenomena that you are focusing on here is the emitted radiation itself, or
the emitted radiation itself is thermalized basically by the Unruh effect, right? And it comes directly from the emission and absorption of Rindler particles from the Rindler bath. That fiducial term, these guys over here, these ones, which ones? So that comes from these ones. It's these terms which come directly from the Rindler bath that enable us to even measure the temperature, wherever this plot is. 1 second. This right here. So what happens is in the co-moving frame, right, I'm accelerating and I'm oscillating transversely while that's occurring. There's the Rindler horizon there, and that oscillation resonantly couples with the Rindler particles of that same frequency multiplied by the amplitude, but of that same frequency. And this was the proposal of showing directly how to measure that temperature from the bath for measuring the Unruh effect. You have the Minkowski calculation, you have the Rindler frame calculation. The Minkowski calculation, and in order for those things to be equivalent, you have to take into account that specific emission and absorption. And so the fact that we even see that is a direct interaction with the Rindler bath, direct interaction. That term is the one that we were even able to measure to measure the temperature for them. Those photons are the ones, so you have the absorption of the Rindler photon and you have the emission. These photons down here, these guys are the ones that are measured in the lab. These ones, okay? You have the pair, if you want to think of it like a particle-antiparticle pair creation. One of them gets absorbed, the other one goes out of the horizon, and the other one gets emitted into the horizon. These are the ones that are actually measured in the laboratory, and they are thermalized at that Rindler temperature, or at the Unruh temperature.
Yes. Okay, sorry, I didn't mean. So I do see that in the inertial frame, this the effect of this excitation or of ND excitation of somehow your accelerated particle in this case give rise to radiation. But the fact that that should have a thermal spectrum as seen by the inertial observer, I mean, the lab frame, that is a less obvious thing. I mean, I wonder whether that depends a little bit on the details. You have this transverse, so the acceleration that is relevant is along the transverse direction?
No, the transverse is basically the one that gives you these photons, but it's the kick. That's it's the radiation reaction is giving you the acceleration. These are very high accelerations. The actual kick from the recoil is where the acceleration comes from.
Okay, which is along the longitudinal direction mostly.
Yes. Yeah. Mm-hmm. So you have a longitudinal acceleration with a transverse jiggling.
Okay. Okay, thanks.
Yeah. And that's that transverse jiggling, that's basically that thing that's been thermalized.
I see.
Morgan, thank you. Quick, but not okay. I like your work. It's very, very intriguing, very interesting. What is the so? Have you talked with the experimentalists doing these experiments and checked with what confidence they think they can see this kind of signal?
So so I have been talking. That's Ulrich Ugerhosch at NX63. Actually, I went up to Aarhus, Denmark, and presented the work to him there. They actually, I mean, if you even look on their, I'll fast forward this one. So they have a lot more data sets that they're working with. And so I've even been talking with them to get a handle on those data sets to do the analysis for those. But just to finalize, this is on their actual website. The concept studied at NA63 even applying a gravitational analog Hawking radiation from black holes, which are meant to be detected, right? And so this is something that they were actually even expecting to see. Mm-hmm. There was even more, what was interesting about it is that they were expecting the transverse acceleration to be the acceleration that was large enough to see this, not from the radiation reaction. And so that was a little bit of the surprising thing for it. And so, so it didn't surprise them that they found it. This is something that they were looking for. The way that it came about was interesting. And we're actually putting forth proposals right now. I just finished, I think it was maybe 2-3 days ago, a big, not a grant proposal, but a fellowship proposal to actually analyze these data, to work with these people, to do these things even in more detail. So there's more data sets out now. They have, this was the highest energy data set. This was at the 178.2 GeV. They have some of the same channeling radiation experiments that are at different lower energies down to like 50 GeV, and then also with different incident beam angles. And so whenever it comes in, if you change the angle, it gives you a bigger amplitude in that oscillation. And so that would be something that's like a smoking gun in terms of confirming that resonant Rindler coupling. And so with the new experiments they have, there's ways to kind of fully flesh out, confirm that the acceleration comes from the recoil because it's at smaller energies, confirming that you are in fact measuring that fiducial Rindler term based off of that oscillation amplitude and things like this. And so this is something that we've put forth proposals for, and we're waiting to hear back and are actually pushing forward to do more. So yeah.
I was actually about to ask about that too, that if you have some way to modulate the gap, right, internal gap, in this case, the transversal oscillation, what gives you the gap, right?
Yeah.
And you can, apparently, for what you're
telling me. You absolutely, and that's something that they're actually doing, and they could do that very precise too. Yeah, so that's definitely something that we're looking forward to doing. Yeah.
Okay, all right. Looking forward to hearing more about it then.
Yeah, thanks.
You said one of the things, perhaps, that to emphasize more when you publish the results, when you can do experiments varying the gap, is precisely, you see that, because I guess it all comes to how well the Andrew DeWitt detector model, in a way, or the model you use, is modeling the physical situation that you see in the lab.
Yeah.
It took me some effort. I have to tell you, I mean, I read the paper and I like it a lot. It took me some effort to actually understand that it was correct. So my first impression was actually, oh, that can be. And it took me a while to read through that, said everything is sound. I mean, I think everything is sound. But the one thing perhaps that maybe the least sound, or at least that I perceive as the one that required more explaining perhaps, is how can you decouple the internal gap from everything else dynamical in the scenario that you have. If that is made really clear in the paper, I think that I could give you, in my full opinion, yeah, you have an experimental detection of the Andrew effect. That's perhaps the thing that is blurring the whole thing, right? freedom to vary the gap. Do you really have it or not? Because the whole varying the energy gap would affect other parameters of the experiment, right? That's the
So okay, so the thing is, I mean, in principle, the actual experiment, what's happening is going to be, I mean, it's very high energy. So is there higher order things happening? I mean, there's all sorts of stuff, right? And so that's one of the reasons why we did the polynomial, okay? And then how we I guess, convinced ourselves that what we were expecting the polynomial to be was what we measured was this. It all came from examples from Cherenkov radiation. Okay, Cherenkov radiation with Unruh DeWitt detectors is actually kind of pretty easy because it's inertial and it's all delta functions, and so doing the math is a little bit easier, right? So if I have a co-moving oscillation, right, this is for the anomalous Doppler effect, right? So just the co-moving oscillation, if I want to incorporate that in Cherenkov oscillation, you just put that frequency in the energy gap, and right, and now you have anomalous Doppler effect in Cherenkov, right? And so the expectation is if I have a co-moving oscillation, that's going to be just a term in an energy gap, right? And this is where we begin to see this with the work that Mathis did on Bremsstrahlung. Like if I want to do pure Bremsstrahlung, it's that zero frequency Rindler particle. If I have a co-moving oscillation, that term is in there as well. So whatever co-moving is occurring is going to be a term in this energy gap, right? So there's that one that we convinced ourselves. Then it was that fiducial term, which you're resonantly coupling with, right? That gives you that covariant description. And then the third one was because the recoil correction to Cherenkov radiation is also known, okay? And that one you could just do pure kinematically. And so that if you incorporate the omega squared over 2m in the energy gap of an Unruh DeWitt detector in the Cherenkov sense with the additional, there's a recoil enhancement due to the index of refraction from the momentum enhancement, but whatever. So if you include that omega squared over 2m in Cherenkov, then that gives you the recoil correction there, okay? And so that was what we were able to build up is there's going to be, so far as what we know from various examples, there's going to be a co-moving oscillation. There's going to be a co-moving oscillation gauged by the amplitude. There's going to be something that looks like omega squared over 2m for recoil. Now, there could be other terms, higher order terms. The cubic term that we put in there, we have no intuition on that at all, just some cross term. So that was what convinced us, at least from that perspective. And then also so that was what convinced us. But at the same time, what are the things that look bad, right? At the higher energy portions of our best fits, the chi-squared actually starts to wiggle. Okay, it's not like it goes and converges flatly to the chi-squared going to 1. It starts to wiggle around a lot, and so is the Unruh DeWitt detector approximation breaking down, right? Because you expect to see that whenever the photons are on the same order of that rest mass, which is the recoil, right? You expect to see that. So is there higher order things that's going on? The higher order quantum effects. And things like that. And so what we think we have is there's the window from the thermalization to some higher order regime where this one is good and we have a pin on everything and everything's okay. But then there's a region where more stuff starts to happen. I think even there was a paper that you had on gauge invariance. We used the V.A interaction, which I believe there's a problem with gauge invariance with the E.X. And so then do we have to switch over? So what we have is that region where things are behaving the way we expect them to behave. And then at the higher end, it starts to wiggle and things start acting weird, which we don't know what's going on. In fact, what I'm working on now with the new postdoc in Seoul is looking at non-trivial dispersion. Is there some crazy dispersion relation process happening in there? And so we're trying to incorporate that now. So I think at the high end of the spectrum, there's going to be a lot of really interesting stuff happening where Unruh DeWitt detector breaks down, higher order terms. One of the things also is there's this paper from Ralph Schutzold about one smoking gun for the Unruh effect is with the 2-photon emission. There's that sweet spot that you can measure these things. And so is there a 2-photon event that's happening that's causing, these problems? So there's a lot of stuff that I think is happening on that higher end, but at least on that one window, from the thermalization time to up to about maybe 100 GeV, things are behaving exactly, in principle, at least exactly how we expected them to. And so that was kind of what convinced us. But yeah, the higher order, it gets weird. Yeah. I feel like there's more physics out there. Yeah.
And I think that's one thing that could put people off at the beginning about the claim, right? The fact that how are they capturing with this model all the physics that's going on here, right? And there are assumptions that come in, and the model definitely breaks. So putting emphasis there, I think, would be very nice when communicating these results, I think.
Oh, sure. Yeah, definitely. Yeah, that was the one thing is the higher order terms is because I always shy away from saying that specifically because I have no idea what what's going on, but I think it's abundantly clear that something is going on there. Yeah. So definitely, yeah, I'll incorporate next time I talk about that. I'll mention that specifically. Yeah.
Wonderful. All right. Thank you.
Yeah.
Sorry.
Yeah. Thank you.